The next problem here we want to go through is a mesh analysis. Now, you can see this from this example here. We have 4 meshes, and we might want to go ahead, call this is mesh 1. So this is I1. This is I2. This is I3. And this is I4. Now, recall how we approach this kind of problem. We notice that I1 in the mesh 1 is given. This is given by the source. So I1 is equal to 6, phase angle is 0 ampere. Now, if you come around the I2, I2 is also given. This is equal to negative 4, 0 phase angle. Because I2 is defined, the direction is opposite to the current. But I4 is in the same direction as the current source provided. So that is 2, 0 degrees of ampere. Now you can see we actually only have one job to do. We need to find I3. So we're going to apply KVL around this mesh 4. And we're going to do that by starting from a particular node. So I'm going to start from here, A, B, C, D. Now, we have a negative 2 times I3. This is from Ohm's law. That's the voltage across the 2 ohm resistor. And again, we apply the passive sign convention. And when we go through the capacitor here, and we notice that I1 and I3 are sharing the capacitor. So, minus of minus J2 times the net current, which is I3 minus I1. Because we defined I3 as the positive direction, because we assume this is a decreasing in voltage right here. Same thing that when we come across this one from C to D, we see a negative of 2 times the net current, and that is I3 minus I4. And finally, we'll come back to A and D, which is the same nodes. And that is equal to 0. So we summed everything up. Now, all we need to do is to plug in the givens and to isolate the I3 and figure out what I3 is equal to. So let's gather all the I3s. This one is I3, this term is I3, and that term is I3. So we have a negative 2 plus J2 minus 2 times I3. And then what are given, I'm going to put in on the other side. And so what we have here, we have positive J2 right here, but times the negative I1. So on this side, that will be J2 times I1. And then negative 2 times negative I4 is positive, but when I move it to the other side, that becomes a negative. So that's a 2I4. And now, we can put what is given in and isolate I3. So now what we have here is we have J2 I1 minus 2 I4, then divided by -4 plus J2. Now we notice that both numerator and denominator carries common factor of 2, so let's just get rid of that. And so we have I4 minus J I1 divided by, now notice here I flip the sign because I don't really want my -4, the real part, to be negative. So I'm going to actually flip the sign by multiply negative sign on both sides, both numerator and denominator. And then we have a -J. So we're going to put everything in here. Remember, I4 is equal to 2. So this is a 2 minus J times I1. I1 is 6. So we have 6 here divided by 2 minus J. So once again, we can do either way. Last time we did changing the phasor in the denominator, but this time we're going to multiply complex conjugate of the denominator. So we're going to multiply 2 plus J. 2 plus J. So we're not doing anything, we multiply by 1. But by doing that here, I get rid of the imaginary in the denominator. So doing that here, the denominator is equal to 2 squared plus 1 squared, that's 5. The numerator is equal to 10 minus J10. So that boils down to 2 minus J2 ampere. Now, after that point, we find the current I3. Notice that the objective of this question is to find I0. And we realize I0 is right here. This is the I0 here. This is the I0 right here across the 2 ohm resistor. So I0 is equal to 2 times I3 minus I4. So finally, we wanted to figure out V0 here equals 2 times I3 minus I4. Since my I3 is still expressed in rectangular component, and that's easier to manipulate in the summation or subtraction operation. So we have 2 times 2 minus J2 minus I4. And I4 is 2. So we have 2 times, inside here is negative J2. Now we just eventually have a -4 times J. Now remember that negative J is negative 90 degrees. So the amplitude is 4 and the phase angle is negative 90 volts. So this is our final answer. But we apply the mesh analysis of the circuits using precisely the same way as we did for resistive circuits.